Laura here, and today we're going over Project 2 for DAT 402. The aim was to use two different machine learning methods on a data set to answer a question of our choice. And the data set I found was from Kaggle by a user named Winter Delta. So if we visit their Kaggle here, they have a link to their GitHub, which explains that their data was from the Kepler satellite telescope from NASA. It's very sensitive to changes in flux, which is a characteristic of stars. It measures the light intensity emitted from these stars. And the idea is that we could maybe use this information to detect the presence of exoplanets orbiting these stars. And exoplanets are planets that have Earth-like characteristics. So the idea is that maybe in the far future, we might develop the technology to travel to these planets and potentially inhabit them, or at least find life on them and so forth. So these data were in the form of two CSV files. The author already separated them into training sets and test sets. So let's take a look here. I decided to use the naive Bayes and the logistic regression with ridge regularization methods on them. And the goal was to see if I could create models that could classify whether or not a star has at least one exoplanet orbiting it in the search for potential Earth-like planets. So let's start with naive Bayes. Of course, I imported my packages and data just like we've done before in assignments. And because the author already separated the data into separate sets, I just left their sets as is. I didn't necessarily shuffle the different observations and then separate them into different sets. So we can see an example of some of the observations here. So the very first column that's just called label, which is maybe not that helpful, denotes whether or not the star has or does not have an orbiting exoplanet. So it's a binary category with 1 denoting it does not have exoplanets and 2 denotes that it does have at least one exoplanet orbiting it. And the rest of the columns are all continuous numerical variables that are measuring the flux value. And for each number in the column name, that's the time interval. So t equals 1 is this column, t equals 2 is this one, and so forth. We can see in the training set that we have a little over 5,000 observations, and in our test set, we have a little over 500. So that's about a 90-10 split, where 90% of the data goes into the training set, and then the remaining 10% is being used to test our model. Our data sets were pretty simple and clean. I didn't really like the way the first column was just called label, so I decided to relabel that one. And then I decided to recode the values from 1 to 2 into a binary 0, 1. Coding, just because for me, I'm used to that, and I believe that just works a little better when I'm comparing naive Bayes to the logistic regression models, although I believe the logistic regression model works with any sort of 2-level categorical variable. So this was not necessary, but I wanted to do it. I also checked for null values, and the author did note in Kaggle that there should not be any null values, and checking here, we can see that that seems to be true, which is great. I checked the proportions of data that had exoplanets versus those that did not, and we can see that this is a pretty imbalanced data set. This is actually the same thing that happened to me in Project 1, so it was interesting to see if I would get the same kind of accuracy results using this method. We can see that for the test data, we have similar results with no null values and similar proportions of yeses to nos. And here, this is just me renaming the column and then recoding the variables to 0, 1 binary. Here I am setting up the model with our training data. Because there was only one categorical variable in this data set that was the output variable, and the rest were continuous, I decided to use the Bernoulli naive Bayes function versus the categorical naive Bayes function that we had used in prior assignments because it seemed more appropriate. We fit our model and predicted on the training set and got this confusion matrix and accuracy score. So our accuracy score is about 0.86, which isn't too shabby. So now we're going to apply this model with the test data to have it predict the test values. And here is our confusion matrix and accuracy score on the test data. So our accuracy score here is about 0.87, which interestingly is higher than the accuracy score on the training data. I found that interesting because I know from lecture, we can usually expect a decrease in our accuracy score on test data and out of sample data. But perhaps because these values are still pretty close to each other, it might not actually be anything too significant. Our false negative rate was 0.4, which might not be ideal, but it wasn't too shabby since for project 1, I had a false negative rate of 1. And here we can see some line graphs of all of our test observations plotted. So the blue lines denote stars that did not have exoplanets in orbit, and the red lines denote stars that had at least one exoplanet in orbit. And here we can see there is a huge variance in flux values for the non-exoplanet stars. And some of them have some interesting patterns as well that don't seem like patterns, while some seem to be perhaps oscillating in periodic cycles. But I wanted to take a closer look at the stars with exoplanets. So we made this graph here, and we can see that the range is much smaller relative to the non-exoplanet stars. But we can see still some variance with particular stars versus other ones. But it seems that we can see some patterns emerging where there's some waxing and waning, and when it wanes, there seems to be a sharp drop in flux value. And this makes sense with what we know theoretically about flux values with stars and how they might work with orbiting exoplanets, but we'll talk about that in a bit. So overall, so far with the naive Bayes, with our over 5,000 observations, we came up with a model that is accurate for about 86% of its classifications. The false negative rate wasn't super high, it was sort of just somewhere in the middle with 0.4. We could see from the plots of the test data that the flux values of stars without exoplanets varied very widely with great peaks and great valleys. But when we look at the flux values of stars with exoplanets, the range is much more limited. And patterns could be seen that would indicate periodic cycles of flux values where they wax and then wane. And this agrees with the dataset's author, who said that stars with orbiting exoplanets could be expected to have flux values that dim periodically due to the shadow of the exoplanet blocking part of the star as it orbits around, at least from our satellite's point of view. And additionally, it may not be as likely for an exoplanet with Earth-like characteristics to be near stars with extremely high flux values, so it makes sense that all the stars that were classified to have exoplanets have these smaller flux ranges because these stars are most likely to have the conditions closer to our own sun, which means that the exoplanets orbiting these stars might have conditions closer to our Earth. So let's see what happens when we apply logistic regression to this data. But here we're importing our packages. This time we are running logistic regression in R, while we did naive Bayes in Python. It's just what I'm a little bit more comfortable with. We imported our sets here. We checked for null values here and then did the same thing as with naive Bayes, where I renamed the first column and recoded the binary values. Here I set up the model and I transformed our data frame into a matrix so that we can use the cv.glmnet function on it. And here we start with ridge regularization. So as a note, I did also try to use lasso regularization on this data, but when I tried to run it with no matter how many folds I chose, and I chose a range between 4 and 10 folds, with 4 being the absolute minimum I could choose. And it would always get stuck in this training phase here at 42% no matter what. And it would just be stuck there seemingly forever. And I've done a little Googling, and it seems that it's possible that it could be from the way the matrix is declared, and that perhaps I need to do a sparse matrix and pass that in that way. But I decided let's just keep going with the ridge, and maybe the lasso one can be done in my free time, because I don't know if it's my laptop and I don't have enough resources or what. So here we can see our graph for ridge regularization. We can see that as our model becomes more complex, our binomial deviance is reduced, and that makes sense. So measuring the performance of this model, we looked at the mean squared error here. And this is our graph here for the mean squared error. And we can see down here that our optimal lambda values, the one that minimizes the mean squared error, was about 0.055. And according to the one standard deviation rule, standard error rule, our lambda value could be 3.03 or so. And here we are now going to predict on our test data. To measure the performance of our model, we are doing that with our ROC curve and AUC value. And we can see that our curve isn't really looking much like a curve. It is lined right up with our diagonal, and our AUC value is 0.5, which is not ideal since we know that the higher our AUC, the better for our model. And here is our confusion matrix and accuracy score on our test data. And interestingly, the accuracy score was 0.99, which, given our AUC value and ROC curve, it seems like there's a little bit of conflicting information. I'm not sure if, despite the accuracy score, I'm not sure how robust this model actually would be compared to the naive Bayes. But our false negative rate is 1, which is also not very surprising in this case given the accuracy score. And this is our GLMnet fit plot. So lots of different variables, coefficients, and lots of different models being tested. So overall, in comparison to the naive Bayes, I would say given the false negative rate, the kind of lackluster AUC score, and the fact that the true negative rate is about 50% of the time, I would say the naive Bayes might be a stronger model for our data set. I'm not sure if the particular method of ridge regularization is the most appropriate for this data set, but I do think, given what we've learned in lecture, that it still might be more appropriate than lasso regularization because of the vast number of features or input variables that we're using in this model. So remember, there are over 3,000 columns in this data set, and each of those time intervals, the flux values at those time intervals, are being used as an input variable. So that's a lot. So given all this, if I had to pick between the two, I would say that my analysis with the naive Bayes method was probably more successful than what I did with logistic regression. So it may just be a question of which type of data are more appropriate for different methods. But I had a great time doing this, and I hope you enjoyed. Thanks for a great semester. Bye.